Okay, thanks Sandeep and all the organizers. This is basically how to cluster tabular data and applications for it, and 2/3 of the talk will be very general. And this is work done by these people. Chandrani worked on a data generation application mainly that I'll talk about, but also the clustering algorithm. Mishit was working on a specific application to DNA sequence, and the work kind of originated in a long-term collaboration with Lilavati, who's basically the person I talk to when I'm stuck. And so what is tabular data? So this kind of thing occurs all over the place, but especially in clinical side, which is what we are currently interested in. So this is the Pima Indians diabetes data set. You can download it for free. And it has like 8 input variables and 1 outcome variable. And the outcome variable in this case is binary. And you can see that some of these input variables are real numbers with decimal points in them. Some of them are integers. Some of them are maybe categorical, not in this case, but they could be. The output variable is categorical, it's 0 or 1. Why would you want to cluster data? And so clustering is an example of what one calls unsupervised machine learning, meaning if you have a data set, what can you learn from it without an already analyzed and classified data set in front of you. So in supervised machine learning, you might, for example, take the outcome variables and then learn some patterns about the input variables that will teach you about this, and then given a new data set, you can predict whether they are diabetic or not. But in clustering, you just want to find structure in your data set. And typically, these data sets have hundreds or thousands or maybe millions of entries, as in the rows. You can think of each row as a point in some abstract vector space, and so you have millions of points. And the dimensionality of the vector space is the number of columns you have. So is there a hidden structure? And if you get a new data item, can you classify it in one of the existing clusters? So that's kind of the motivation. For example, you might have a data set like this, and eyeballing it, you see some structure already there. And now if you feed it through, let's say, a k-means kind of algorithm, actually I don't know what they used here, but it kind of picks out maybe the structures you already saw, but depending on the algorithm, this particular one gives a different color to these 4 points, a different color to these. So you might not know a priori how many clusters to expect, and you might not know, you might want a way to assess that also, what's the reasonable number of clusters to put. And then having decided that, how do you decide whether to classify a point like this as red or blue? So it's, there are many different algorithms that do this. These are some examples from the scikit-learn library in Python. This is from their web page. And so these are a whole bunch of algorithms that are implemented in scikit-learn, ranging from k-means, where you're basically looking for centroids and assigning each point to its nearest centroids, to Gaussian mixture models, where you are modeling the entire data set as a mixture of Gaussians, agglomerative clustering, where you're sort of building a phylogenetic tree. But as you can see, depending, each of these represents a data set which, in the most cases, your eye picks out a reasonable clustering. But some algorithms work well with this ring structure, like agglomerative. These are also variants of agglomerative, but k-means does terribly with this. Or with this structure, plain agglomerative doesn't work well, but dbScan does. There are other algorithms where everything gives you a reasonable answer. This last example, probably there is no ground truth structure, and some of the algorithms just report that for you, but some of them just pull out some structure. So that's sort of the, so the zero order message is that there is no perfect algorithm for clustering. Depending on the data set, some algorithms do better than others. With that, our goal is to cluster the sort of tabular data set that you saw in the last column. So, so this is something we recently did, and I'm rather proud of the name, Madras Mixture Model. Essentially the idea is you are clustering this kind of data set where the columns can be numeric or discrete. So there are other kinds of variables like ordinal, like 0, 1, 2, 3, or cases where there is an order to the columns. We are not considering that. We are considering categorical, where you can have 2 or more categories, and we are considering numeric variables. And the categorical variables are assumed to be drawn from some unknown distribution with a Dirichlet prior. I won't explain all that, but People who have done my courses might know it. It's a simple thing, and the normal distribution likewise a normal gamma prior. So these are the conjugate priors for the respective distributions, and it makes the integrals easy basically. So the idea is that if you're trying to cluster into k clusters, we are trying to find that clustering, that choice of labels, of cluster labels to rows, which maximizes the likelihood of the data, that is maximizes that the rows with label 1 actually belong to that cluster, and I mean they are drawn from the same underlying distribution. The rows from label 2 are drawn from a different underlying distribution which is different from the cluster 1, but they are drawn from that, and so on. So we use a sort of EM algorithm where instead of doing the M step we integrate out. So again I won't go into the details. And the other contribution we have is, so it is well known that marginal likelihood, that is the likelihood that we are calculating here but integrated over all parameters including cluster assignments, basically gives you a good estimate of the optimal number of clusters. It prevents you from overfitting, because just this will give you a better and better likelihood the more and more clusters you make. So at some point you have to say, no, this is over complex. This is known to be good, but it is expensive to calculate. There is a method called thermodynamic integration which was published by, sorry if I get his name, that Columbia guy. Which is inspired by physics and very accurate but slow. So we propose a faster way to approximate it, which is pretty accurate. Our benchmarks on synthetic data sets, these are purely numeric data with uniform mean and different variances per true cluster. And then this is purely categorical, and there's a mixture. And in all cases we do pretty well. For numeric data, the Gaussian mixture model also does well, but if you have a mixture of categoric and numeric, we clearly outperform everybody else, and that is even if we don't know the true number of clusters, we are estimating it with the k that we are using with the thermodynamic integration or the HM beta thing. Either way we do quite well. Okay, so this is on synthetic data, and on real data sets from a database called ClusBench. So here there is no true cluster assignment. Instead, these are meant to be machine learning tasks, and there is an outcome variable, like in the diabetes data set that I showed you, which is also part of this in fact. So the output variable is 0 or 1, and we are clustering the data set excluding that last column, the output column, and seeing how well it agrees with that classification. In many cases, it agrees very well with that, suggesting that the inherent cluster structure in the input variables is something useful to predict the output. And the second part of this work was generating synthetic data sets from tabular data, and this is something that people have been working on in recent years, especially in the context of clinical data where patient confidentiality restrictions make it very hard to share data sometimes. So what if you could take your data, generate a synthetic data set that is in every way equally good, so to speak, in that you train an ML model on it and run it on a real data set, you'll get equally good predictions. So there are a few publications like that which use basically deep learning. Instead, we do something much more simple. We cluster our training data set and we train a statistical model on each cluster separately, and because each of them is just modeled as a mixture of normal and categorical distributions, and then we simulate using those parameters, and then we mix it all up together, and that's our synthetic data set. And we benchmark them against those previously published methods, and we basically, with a very simple method, we come pretty close to the real data performance, and the only method that sometimes outperforms us is TVAE, but basically we are doing very well with this. Right, so that's basically the Madras mixture model, and a possible application of this is some work we did some years ago. It doesn't use the same algorithm, but it is basically clustering DNA. So the idea is that you have a particular type of DNA data called ChIP-seq, which is data that tells you which regions of DNA a particular protein you're interested in might bind. And the data set might look like this. It is just a bunch of ATGC sequences, and our clustering algorithm clusters this into patterns. It more specifically clusters windows of this into, and these are the labels that our output here. And you can visualize the clusters like this, and I won't explain in detail how it goes, but basically this is, instead of an exact string, you see this kind of pattern. So a tall C means you almost always see a C there, and a mixture of a C and a G means you see both of them equally often, and so on. And this was from the 2017 paper, but right now Ishit was been refitting our MMM thing to work on DNA specifically. It's purely categorical variables with 4 categories, and it looks like it is doing much better than our previous program, which was already doing better than many of the published programs. So that's something to look forward to. So yeah, thank you very much.
Thanks a lot, Rahul. Do you have any questions?
Suppose your data set is very noisy. So how do you generate this synthetic data? If you can you do some way to remove noise or something?
Yeah, so the noise is part of the data. So your synthetic data should also be noisy. That's a feature and not a bug. But that reminds me that sometimes your, especially in clinical data, you might have missing values, and then there are standard methods to interpolate the missing values. We don't do that, but there are things in scikit-learn that can help you do that. So that's a sort of separate question. But also in terms of noise, sometimes the data is just wrong, like the medical entry person put in a height of 19 meters instead of 190 centimeters, and so those you should, there are ways to screen for outliers and reject those points, so that should be done.
You can have like a
Missing nucleotide. Sometimes you see an N which means you don't know what that nucleotide is, but so we deal with that because it's just one variable. Yeah.
So I have one question. So in general, of course, many of the data sets that we study, we do see that also in reported biology that you may have only some relevant features, which is a very tiny fraction of the total number of features. And so if that is the kind of data set, then how do you do clustering? Because we kind of tend to think that if you use only those variables, those features, then only you can cluster properly.
That is actually what Leelavati is working on. And in fact, she gave a talk here about 6 weeks ago. So that's a thing called feature selection, where you select the relevant columns. We are not really doing that here, and hand-wavingly, you could say that the relevant features won't contribute to the clustering. The likelihood will be pretty much the same no matter how. So that's why we do reasonably well, but even if, as in the DNA case, the most of the important features are only this much out of a much larger sequence. But yes, if you can do feature selection, you should do even better.
Okay, thanks a lot. Yeah. Okay, our next speaker is Vaiva. So.